Hi, Srini.
Hi, Chair.
How was your day?
Fine.
How was your day? Fine. What did your teacher do today?
Okay.
Okay, let's just review it again. Sorry about that. Okay, so that's your syllabus. We start with principle of superposition. Right. That one, principle of superposition, you have to memorize it. You'll be using it. When waves meet at a same point at the same time, the resultant displacement is the sum of the individual displacement. Right? We are looking at a particular point, and as the time changes, as the wave passes through a point, there are two waves there. Remember, there are two waves passing a point. You want to look at the waveform at that point there. Right? We add the displacement, like in this case there. One traveling, the pulse traveling to the right, one traveling to the left. So as they start to meet, you can see there's a start adding up with it. Right? This part going to the left, part to the right, you add up, you get the resultant waveform or resultant pulse. So as they separate, they become a separate shape again. Okay, so just to review you, resultant displacement. Right? Remember, displacement a vector quantity. If we take ours as positive, then downward is negative. So in this case, we can draw our 10 meter upwards displacement, and downwards 6 meter. So the resultant is 4 meter upwards. Or it can be in different same direction, 10 meter upwards, and another one other. Right? Remember, we are looking at two waveforms. One is 10 meter upwards, one is 6 meter upwards. So we just add 10 meter, then 6 meter, and the resultant is 10 plus 6 is 16 meter. Right? Intensity is slightly different. Intensity is proportional to amplitude square. K is your constant. Right? A is amplitude. You can write that in equation form. I equals to Ka squared. Right? As its amplitude is A. If it's double, then we replace this A with 2A. Right? A with 2A, double the amplitude. So this becomes 4A squared. 4A squared. Ka squared is I, so it becomes 4I. 2 squared is 4. Ka squared is I. Right? You can associate intensity like loudness, louder. Right? It's just illustrate the same thing. Right? These are, we are just adding at a point as well. These are the wave going to the left, this going to the right if you like. And then at this point, that's what we see. Right? Yeah, usually we are interested in two particular one called constructive interference or reinforcement. Right? Where the crust or trough of two waves coincide. We are looking at same frequency or same wavelength. Where the crust of the two waves coincide. The two waves are in phase. Another way of saying they are in phase. Exactly the same. They combine together to create an amplitude wave that is known as the constructive interference. So this is the wave. Remember, they are on top of each other. Right? Where they coincide, we add up, that's what we get. Right? Only at a particular time. If the wave have amplitude A, intensity I, the resultant as we have calculated, resultant amplitude is 2A. Right? Add it up, is A plus A is 2A. Then the intensity is 4 times. Right? The individual intensity. If it's light, if the two waves are light, then we see brighter light. Or if it's sound, we hear louder sound. Okay, the amplitude is the one that changes. The frequency still remain the same. Right? This wave frequency is the same as both of them. Right? It doesn't change the frequency, change the amplitude only. Right? This is just to illustrate to you, to impress on you. Right? The red one and the dotted one, right? Which is traveling to the left, are on top of each other. And then we don't see them separately. We see them as the resultant waveform. Two waves passing the same region. Right? We see the blue one, not the individual one. Right? That's the resultant waveform. Question: if the amplitude of wave is A, intensity is I, what is the resultant amplitude in terms of intensity? Right? See, we have just gone over that. It's just to work it out for you. This is for one wave, that's the intensity. Resultant amplitude, A plus A. Right? A plus A is 2A. Resultant intensity, K, right? Instead of A now is 2A. A. Right? So it's 4I. Right? We have done it, we are just repeating. And the other one is destructive interference, right? Same frequency, the two waves on top of each other, right? Same amplitude. We get a destructive interference, or we call it cancellation. When the two set of waves cross, right? This is where the two waves cross, where the crust meet the trough. Right? That's the crust meet the trough there, or the crust meet the trough here. Or another way of saying is they are 180 degrees out of phase. Right? This is maximum, this is minimum, this is maximum, this is minimum, 180 degrees out of phase. Right? If we want complete cancellation, right, 0, then the two amplitude must be the same. If there's a little bit of amplitude, right, different amplitude, then we will have a small waveform here. Right? There will be a resultant waveform. Right? If it's light, we see dark or dark band. We will study later on. Sound, we hear no sound. Okay, so this is lastly the same thing again. Right? Two waves, one traveling to the right, one traveling to the left. The red one traveling to the right. Broken line traveling to the left. So this is constructive interference. And what we will see, the two waves passing the same region at the same time, we see the resultant waveform, 0. You don't see the other two waveforms anymore. Okay, for this another picture, same thing. Except this one show the two initial waveform on top of each other at a particular time. And then there's the resultant waveform. Right? 0 amplitude. Okay, so we have just completed all that. These are the extra things that you need to remember. Principle of superposition, what is constructive interference, what's destructive interference. Let's go to standing wave now. Right, page 58. Use principle of superposition to explain the formation of standing wave. Derive and interpret the standing wave equation. Distinguish between progressive and standing wave. Rather than just teaching you about standing wave, no relationship, I thought I would cover 21.1. Use standing wave equation to determine the position of nodes, antinodes, or standing wave on stretch string, right? To help you understand this part. If not, it's very hard to see. If you look at the theory only, the maths involved, without looking at real life situation. Right? Condition for standing wave, for forming standing wave. The two interfering periodic waves must be traveling in opposite direction through the same medium with equal speed. Right? The two waves, the red one and the blue one, Right? You can think the blue one is moving to the right. The red one is the one that is reflected. Same speed. Oh, that's same speed because they are from the same source. Same wavelength, either wavelength or frequency. Same amplitude. Same time. That means light and light, sound and sound. Cannot be light and sound. So if this condition is satisfied, then you can form standing wave. Oftentimes we go to seaside. If we see a river flowing out to the sea and the sea coming to the land, we may see this type of sand accumulate and then deeper there. This is where standing wave is formed. Right? This is where the node is, where it doesn't move, the soil doesn't oscillate. Whereas this part, remember the wave is coming in, going out, coming in, going out. So this part is vibrating. At the node there, it's vibrating up and down. So that's why the sand is pushed to this side or that side there. Onto another side. That's what we can see in real life situation. This one is in Scotland, taken from internet. Okay, progressive wave. Right? We look at the particle motion as a wave passes. Right? That's the original wave. Right? This is the water, if you like, the water. Right? A short time later, this is a short time later. Okay, you can see that this wave, which is at this particle, the maximum is now going to the 0. Or this one at 0. Previously, when the wave is passing, now at this stage is moving to the maximum. As the wave moves through the medium, each particle oscillates at different phase. Okay, here you can see this wave or that wave. The particle here and the particle here and the particle there are at different phase, different position, different height. Or we usually call it phase, different angle, right? Different phase. It hasn't, this one reached maximum amplitude. This one hasn't. This one hasn't. This one is 0 amplitude. When the particle is oscillating to and fro continuously between two fixed points, we say that the particle is in simple harmonic motion. So what is happening? As the wave passes through, right, there's another position a short time later. Right? If you look at a particle here, initially, when the wave passes, it is 0. Then after that, the wave passes, it goes to maximum. It oscillates to maximum, then it goes down. Then continue up and down. Or you look at this particle, it will go to here. It will oscillate downwards there. This particle here will oscillate downwards there, then go up there. Okay, or you can take this particle. Same thing here is 0. Now it's going to that part there, then it's going down. Right? So you continue looking, it will going up and down. There's your two fixed point. Bottom and up. So it's going up and down. This is called simple harmonic motion. So each particle will be going simple harmonic motion, but they are at different position. They are not in phase. That's what it means. That's a progressive wave. It's keep on moving. That's what it means by wave. Progressive wave. Okay, let us see how the two waves traveling in opposite direction form standing wave. Red is moving to the left. Blue is moving to the right. You can look into your book, page 60, 61. Refer to that. That is the blue one. That's the red one on top of each other, where at time t equals 0. So we add them up, this constructive interference, we get the black one, resultant waveform. Right? A quarter of period, right? Remember, the period is from here to here, if you like. So a quarter of period is just one of these section there, a quarter there. So the red one will move there, right? Peak is here, move to there. The blue one or the broken line will move to the right, quarter of a period, that's where it is. So now it becomes destructive interference. Right? 0. Remember, the waveform doesn't stop here or doesn't start here. Carry on continuously. So I complete for you. Right? And another quarter of wavelength, the red one, right? This one will push here. This blue one will go to here. Right? So a quarter of the another quarter. Sorry, this one should be half the period, not quarter. Another quarter will be half. Sorry, what is happening? Okay, now Srini, any question you want to ask?
No, teacher.
Right? 1/4 and 1/4 is half, no? Okay. Okay, so that is your quarter. From 0 to a quarter, another quarter will be half. Right? So the blue one will have moved to a quarter. The red one will move to another quarter there. Okay, remember, just imagine is the wave is continuous. It's not like a blank here, you know. So it's disruptive interference again. Okay, except this is previously is going down, now it's going up. Right? We look at the point here, it's going up and down. Look at this point there, it's always stationary here. Concentrate on the black one. Black is the resultant that we see. Right? The red and the blue are the original waveform, but we don't see them. Right? We see the black one. Black is what we see. So initially, it is going down, and a quarter period, it goes to 0. All of them go to 0. Right? All of them oscillate together. Its bottom goes up, then goes up again. Okay. So that one goes to maximum. Remember, all of the particles, all are in phase from here, within this region, these two regions there. It is all moving up together. These are all moving down together. Okay, so this one just summarize to you the same thing, all to compare for you. Right? Just to look at the picture again, but now I am just concentrating at the resultant waveform. Right? That is the, if I start with t equals 0, this one, right? If you like, I'll take this part. Right? This part. Right? Concentrating on this part. Just a small region there. This one. At t equals 0. Right? What is the phase difference between the particle here and the particle here? Yep. What's the phase difference?
From where, teacher?
A particle here, and a particle here. What's the phase difference?
Don't know, teacher.
One is up, one is down. Yeah, it's going like that. All the particle here is down. All the particle here are up like that. So as the wave pass through, it will go like that. That's all. So also like that. Right? That's why I'm trying to show you the different stages. So that is if we are looking at this region, that rectangular region. So this is where we see the waveform. Now we see 0, a quarter of the period later, and half the period is that's what we see. That's half the period. That's what we see. That one there. Okay. So all these are in phase. Right? They move at the same time, except that the largest amplitude is here. Right? Other particles between these 2 points there have different amplitude. Same here. All the particles are different amplitude. The largest amplitude is just here at the center there. Like same here. Right? But the particles here and the particles here are 180 degrees out of phase. That means this is going down, this is going up, this is going down. That's what I mean by 180 degrees out of phase. Right? And we give you a special name N, called node, N-O-D-E. And then where the amplitude is maximum, we call it antinode. A. So summarize that. T equals to 0. That's the waveform, the resultant waveform. And a quarter period later is that. Another quarter period, which becomes half, to be that. So N is the node. It's a point that's permanently at rest. That point is not moving at all. You can see that as the standing wave is formed. It's not moving at all. It's always 0. Always 0. Only the point, the middle point there, the midpoint there, A here, will be at large amplitude. Right? We call that antinode. It's a point that has the largest amplitude of vibration. Okay, between NN, right? NN, the particles each have different amplitude. Right? All these different amplitude. Largest is at the center here, so then sorry that there's a poor drawing. Right? So between NN, the particles have all different amplitude. Largest is at A. And that's your wavelength. When you want to read a wavelength, you look at either the black one itself or the blue one. Okay, don't mix them up. But when we draw to differentiate between standing wave and progressive wave, that's how we draw the two waveform. Right? And from 0 to 0 is half a wavelength. From 0 to maximum is a quarter. Right? From 0 to maximum, or from maximum to 0 is a quarter wavelength. Okay, so this is just to stress to you, between the node, the particles are in phase. All of these particles are all upwards there. Right? That's why I say vibrating in phase. Whether the particle here or the particle here, they're all in phase. Right? If you compare the particle here and the particle there, they are under 80 degrees out of phase. Okay? They are under 80 degrees out of phase. 10 more minutes. Right? Or you can think of this particle here and the particle here, they are 180 degrees out of phase. Alright, and know how to identify that's half a wavelength. This is a wavelength. Right? A quarter wavelength. Okay. So let's just summarize the terms. Standing wave showing different stages of vibration. Nodes, right? Where the end there. Then there. Points where the displacement is permanently 0. Antinodes, center there, midpoint between the two nodes, are points that have the largest amplitude of vibration. Distance between two successive nodes, right? These two distance is half a wavelength. Distance between a node and an adjacent antinode, a node, adjacent antinode, or node and adjacent antinode is just a quarter of a wavelength. Okay, this is just to repeat to you, to stress to you. At time 0, if it's maximum, then a quarter period, that's what you will see. Right? Gray is moving to the right, black is moving to the left. We see the blue one only, the resultant. We won't see the individual waveform, only when they separate outside. Right? So next stage is just 0. Resultant is 0. And then the next one, same thing. Right? You'll be vibrating. The resultant is this way. Right? Previously it's minimum, now it's maximum. I'm just repeating, just to stress to you. Right? At antinodes, the waves are in phase, thus constructive interference occur. resulting in maximum amplitude. At nodes, the waves are 180 degrees out of phase. So the destructive interference resulting in 0 amplitude. Okay, it's just to stress to you the different stages. We start from the bottom here. Is all of them is moving up to here, then come down again. This one is moving up, all here, moving down together, and after that moving up again. Okay, so it depends where you want to start. You will start from here, then a quarter will be here, half will be here. Then for this part, half will be, the T0 is here, and a quarter is here, is half. Then we identify the node, antinode, then we identify the wavelength, right? 0 to 0, and then this is half wavelength. From a node to a node is half a wavelength. From a node to antinode is a quarter of the wavelength. Right? Node to antinode, N to A, quarter of a wavelength. Okay, so we are going to do that. That's why I'm saying to page 81. Can refer to that. But let me just make a start. We still got a bit of time. So we take a break. Right? A person there. There's a string attached to the wall. Right? Can swing horizontally. That's what you see. Right? A first loop. Then you increase the frequency, you shake harder, faster. Right? You see 2 loops there. Higher frequency still, you see 3 loops. And then higher frequency still, you see 4 loops. Right? This is 1 loop. This is another loop. Okay. Right? Or you can do it more accurately using a vibrator. Right? And then right? Signal generator. The vibrator is joined to a signal generator. This one. Vibrator is just causing it going up and down. That's all. Cause the end of the string to go up and down. Vibrate. Frequency of vibration can be controlled by signal generator. It can connect to a signal generator. Right? This one provide a alternating current of known frequency and peak voltage. Vibrator cause the end of the string to go up and down in simple harmonic motion. So you send the wave down. This is a fixed end. Reflected backwards there. Hanger and slotted mesh. This one hanger and slotted provide the tension. Right? Provide the tension in the string or wire. This determines the speed of the wave. Okay, so the speed of the wave in the string is determined by the wire. We call it mass per unit length, and the tension in the wire. Right? So this vibrator will send the wave to the right, and at the pulley there, fixed end, will be reflected. So the incident and reflected wave interfere to give your standing wave. Right? You don't see the individual wave. You see only the resultant waveform called the standing wave. For fundamental mode, the mode occurs at the end of the string. Okay? This is destructive. Right? We will look at fundamental mode. Nodes will occur at this point there, and this point there, and where it attached to the pulley. Antinode will be at the center there, right? Midpoint between the 2 nodes. Okay, so that's a formula you need to remember that determine the speed in the string. Okay, mu is the mass per unit length. Right? So the speed is constant, determined by the tension in the string and determined by the mass per unit length of the string. Or it can be wire. It doesn't have to be a string, it can be wire like guitar. Okay, so we will see this different mode. So I'll stop here. The next part, I'll go to derive for you the different, how we get the 1 loop, 2 loop, 3 loop, and 4 loop there. So anything you want to ask, anything that's not clear, you still got a few minutes.
So far, nothing.
So far, nothing. Okay. You can look at the 20.3 and 20.4 in your checkpoint. And then if you want, you can take 5 minutes break. We still got time, then look at the checkpoint there. Try to do some of the problem. Okay, I'll stop here.